Good morning, sir.
Morning, sir. How are you?
Very fine, sir. How are you?
Fine, fine.
Okay, so, shall we start with your permission?
Yes, sir. We can definitely start.
Okay. So, dear participants, welcome back to the workshop. We have our expert with us, Dr. Nitin Kumar. He is working as associate professor in the Department of Computer Science and Engineering at Punjab Engineering College, Chandigarh, since May 2023. Earlier, he worked as assistant professor in Department of Computer Science and Engineering at NIT Uttarakhand during July 2013 to May 2023, 10 years. Currently, he is professor in charge faculty affairs at PEC Chandigarh. Before this, before this assignment, he has shouldered several administrative responsibilities at NIT Uttarakhand, including head of the department, coordinator faculty development and continuing education, coordinator industry institute interaction and brand building, coordinator institute voucher and newsletter, and coordinator of student admission and registration. Dr. Nitin has obtained his BTech from Kurukshetra University, MTech and PhD from JNU New Delhi. He is GATE qualified, UGC GRF qualified, and working in the area of pattern recognition and machine learning, biometrics, data mining, image processing, visual attention modeling for more than 13 years and has published 72 research papers, out of which 39 are peer-reviewed journal, including 32 publication in SCI, SCIE index journals. He is currently He has successfully supervised 6 research scholars for their PhD degree. 2 research scholars are currently pursuing their PhD degree under his supervision. He has also completed a sponsored project as HPI. He has delivered more than 20 expert lectures in reputed institutions, including NIT Kurukshetra, NIT Uttarakhand, Punjab Engineering College, CDEC Mohali, CSIO, etc. He has received several awards at state, national, international levels. He is the recipient of Young Scientist Award by Uttarakhand State Council of Science and Technology. He has been elected as Fellow of IET New Delhi in December 2023. So with this introduction, I invite Dr. Nitin Kumar to deliver his expert talk. Over to you, sir.
Very. Thank you, Dr. Abhishek, and for inviting me for this expert lecture. And I'm very thankful to all the team members also for conducting this workshop. And what I feel from the title of this workshop, on artificial intelligence and computational imaging in healthcare. So AI has become a buzzword, like everybody knows, and the applications are never ending. So daily we are listening about new and new things which are being done with the help of AI. And healthcare is a vital component of anybody's life. And this healthcare advancements you might have seen, one example I start with, like this cancer treatment. So if we go back 20, 30 years back, there was nothing that can be done, that could have been done 20, 30 years back. But nowadays, like, at least a few treatments have come up, and that too with the advancements in healthcare sector. But how AI, how artificial intelligence can help in this healthcare sector, that is the motto of this workshop. And that is the contemporary things that have been there in the workshop. And this workshop is being organized by CSIR, as all of you know. And I will be delivering a talk on random permutation principal component analysis. Very long title, so you will be thinking, what is this? Okay, so mostly it is we will be talking of the biometric, what is biometrics, and how this biometrics is helpful in healthcare sector, and how we can enhance the security of biometric itself. Okay, so this is a double secure system, like that will be seen. So like biometric is basically used to identify people. Okay, so that I will be discussing one by one. So initially, this what is biometrics? How am I audible to everyone?
Yes, sir, you are audible.
Okay. So this
Yes, sir, you are audible.
uh,
Just a minute.
this
I think a few participants has opened that one. Let me.
participants are requested to mute their mics for some time. So
I have done
uh,
it, sir. I have done it. Forcefully, I have done it.
okay.
No problem. You
So
can see it.
initially we'll be discussing about the biometrics. So what is biometric? How does we know something can qualify as a biometric or not? After that, we'll see that how biometrics are helpful for the healthcare sector. We'll also see few problems with the traditional biometrics that I'll be discussing, how we can solve them with the help of cancelable biometrics. So that is a relatively newer domain. In recent years, there have been a lot of work in this field, and we will see two methods like very basic, very popular methods like the principal component analysis, that PCA, and the two-dimensional principal component analysis for that, and how this PCA and 2D PCA, these are the traditional methods of how we can enhance their application for the cancelable biometric domain. And lastly, we'll see how we can measure the performance of both of these methods and what are the results that we had done few experiments on this, and how these results are better than the state of the art methods before I conclude. So if I just start with a simple question, so with recognition, and I draw a random kind of object. So anybody recognizes what is this? What this object means? No? So if I say draw something like, say maybe this, these are some of the arrows going, but if I just start with this, anybody can recognize this shape? Yes? Okay, you can respond.
This is square. This is square or
This is a
rectangle.
this is a square, this is a circle, but this shape we all may not be knowing. So recognition something is that if we want to name something, if we want to identify something, then it is the first thing that we must have seen that shape or something before we can recognize something. Like if you see any person the first time, in that case you may not be able to recognize. But if you have seen the person, maybe you have met someone, you have seen the person somewhere, either physically or on some news channel, then you can identify, yes, that this person is there. Okay. So recognition basically is a activity, it's a mental process of knowing, including aspects, okay, like awareness, perception, reasoning, and judgment. So if we have encountered something before, and again we are trying to encounter that same thing afterwards, so that we are like we are actually calling it as recognition. Okay, and this recognition is part of cognition. So that process that is underlying this recognition is the cognitive part. So where we are trying to get aware about something, get perception about something. Okay, so this recognition is an awareness that something we are perceiving that has been perceived before. Okay, so only those things can be recognized which have been seen earlier. So like biometric is also the same part in that direction. So if I want to identify something, okay, so there are few methods. Like if we talk about the traditional methods, so like this is the thing by which when there is a uh, you can say connection between the human being and the machine. Okay, just like you have some lock, there are some keys. With the help of keys you can get something. So that key is basically enabling you to identify that some authenticated person is having the key. Okay, so something you have, so that was the first thing with the help of which person can be recognized. Or you are possessing some kind of document like your passport, your like your driving license, something you are having, you are possessing that, and that enables you to do something, that enables you to get identified by any other person. After that things have changed. So these are the things of a very past, like before computers came into picture. Now when the development happened, and computers came into picture. So then instead of this having physical keys and physical documents, now there was a paradigm shift to have some kind of codes, okay, just like your passport as a password. Like this, it can be any one simple password is written. So all of you have passwords nowadays, whether it is your Gmail, whether it is your uh, any kind of email or any other kind of, you can say, secure system which is inside your organization, so that you want to access. So you have some login ID always, okay, login user ID and password is there. If you have that, then you can log in, then the system will recognize. But if you don't have that or you forget, then there is a problem, you will not be recognized by the system. Similarly is the pin, same way code we can have. But what was the problem with this something? So like if we have these keys, okay, they may be lost somewhere. Somebody may steal this passport, okay, and then you will be left with no option, okay, but to waste your time again, visit that passport office, put some complaint, okay, that I have lost, get a copy of FIR, etc. All that process, long process, so a lot of time wasting. Then something I know, so if I have some password or code like pin, so that can also be stolen. So that there may be some also phishing websites, so that these passwords or pin may not be secure. There may be system like which are tracking the screen, okay, or your keyboard. So anything, so something I know. So if you, even if you forget or something has stolen that password also, you have forgotten your password, still you will not be able to do the things. So very recently, like after this, there was again a paradigm shift, and now the objective is that can we recognize a person without, can we recognize a person without having any kind of physical thing or some password. So it is the person itself, okay, so person will present himself or herself in front of the machine, and then we can say that the machine will recognize whether the person is authenticated or not, okay, person is same as the authorized person or not. So now something I am can be done with the help of different kinds of traits, okay, like fingerprint is there. So most of you have this fingerprint scanner on the mobile phones, and you give whenever you enroll for the fingerprint. So you give several samples, okay, like 8 to 10 samples you give in different directions, okay, up and down, left, right, like that. So you give 10 different samples, and after that enrollment has been completed, and you want to log in into your mobile, you simply put your fingerprint onto the scanner, and then you are allowed. So how does that mobile knows whether you are the same person or not? So I have tried it. You can just try this. So if any other person wants to access, he or she will not be able to access the mobile phone. So like that. So a person himself is presenting. So this is one example. Similarly, we can have the iris. Okay. This fingerprint scanner is very easy to integrate into the mobile phones. Okay. Like camera is also there. So iris pattern can also be integrated. Similarly, we have DNA, okay, and face. That is the most popular thing. So face you have been using since your childhood. So face is the uh, biometric which is used by most of us, okay, to recognize one another, okay. And the domain shifts, like if somebody is like differently abled, so maybe he's not possible to see anyone, but he can recognize the person by voice, okay. So voice is also qualified biometric, so that can be used. So like why we are talking of this biometric is because of these reasons. These there are some characteristics, okay, why we are using biometrics and why they are helpful, okay. So if I just talk about its beginning, so it started with two Greek words basically. So bio means life and metrikos means measurement. So we are trying to measure the life, okay, life in the physical sense, okay. Any physical or behavioral characteristics which can uniquely identify a person. So this word uniquely here, so that is very important, okay. Uniquely identify a person means we should be able to identify the person in a unique manner. So there are some distinguished characteristics that are possessed by every individual, so based on which we can identify. And these biometrics, these characteristics are typically divided into two categories. One is the physical and another is the behavioral. So now how do we see whether some trait, any kind of trait is qualified or not? Like if I ask you that based on skin color, any person can be identified. So you will find that a lot of people have the same skin color. So the distinctiveness is not there. Okay. So these some of the properties. Like universality means all people should possess the biometric. Like the largest project in India, that is the Aadhaar, so that UIDAI, so that ID card is being issued, and sorry, people are enrolled for like facial image is taken, iris pattern is taken, fingerprint pattern is taken. So that is an example of a multimodal biometric, and that is a once these are put in the system, then anytime they can be used for the person recognition. Okay. Distinctiveness, as I told you that if I take skin color, maybe the properties is not that distinctive, so that will be very less qualified. No doubt it can be used as a additional information about some person. So if you want to detect someone, but it is not the primary trait that can be used for uniquely identifying a person. Permanence means the biometric should be permanent. Okay. So there are some issues like the people who are doing the labor work, maybe their fingerprints are eroded away after few years. So that creates an issue. But like face is a permanent thing there. So if you have heard about like ear can also be used for recognizing any person. Okay. Collectability means we should be able to collect the samples and it should be acceptable by most of the population. Okay. So if it is like something pierces the body, so then it is having less acceptability, just like the injection. Okay. In healthcare, if we talk about, people are less susceptible that we should not be injected anything, you know? So like performance, the performance of that biometric should be very good, and circumvention means it's the technology that we are using for identifying any person, that should be difficult to deceive. Like if I give you if I give you a sample image that is a drawing, okay, only the sketch of an image, then system should not accept that sketch. Otherwise, the system will be having problems. It can allow anyone whose sketch is presented to the system. So these are some examples here. So physiological biometrics based on the physical characteristics like face, iris, ear, hand, fingerprint, DNA, and the behavioral characteristics which are shown in our behavior, like the gait, how some person walks. Okay, some old person can detect anybody with the help of gait or voice. Okay, just I told earlier. Gesture also, how somebody is using the gesture, hand movement, signature, keystroke, and handwriting, etc. So these are some of the examples. Now the question is that how we have got something to know about the biometrics. The question is how these biometrics are useful in healthcare. Okay, so if you see, one aspect of healthcare is like we are treating someone. Okay, or like nowadays there have been a lot of like health insurance is there. So some person is getting treatment at some say hospital. Okay, so how do we ensure that the person who is getting the treatment is the same, say, whose insurance has been done? Okay. So there need to be some mechanism with the help of which we can identify, yes, this person is the correct person based on the biometric information, based on the login system. Just like everywhere you see Aadhaar based authentication is there, whether the person is the same that the system is recognizing or not. So you are in most of the applications nowadays, you will be asked to verify yourself with the help of Aadhaar ID, and then some OTP will be sent. Then you are authenticated. Yes, this is the correct person. Similarly, if we see, so patient safety, we can improve patient safety through accurate identification. Okay, so like if there are two people, okay, with the same name who are visiting a hospital, and it is probable that their reports may also get mixed. Yes or no? It is probable, but with the help of biometrics, if we have some biometric system in place, so person has the authenticated at the time of say sample collection, person is authenticated using the biometrics, so these medical errors can be removed. Okay, so it is also useful in eliminating the duplicate records. Okay, so some person has visited the hospital some time earlier, so again a new, instead of creating new ID, old ID can be used, so enrollment can be done at the hospital levels also. And it also ensures the accuracy, that the accurate information is available to for every patient that we have. Okay, so and this enhancing security and preventing fraud, so that's what I was just talking. So data access, so any data that is related to medical history of any patient, that is very important. Okay, so and that data needs to be secured using some means, so either you or the hospital administration only should be able to access that data. Okay, otherwise there may be some cases of data leakage. Okay, like the people who want to harm you, so they can, if they are having access to data, then they will have your weak point. So where, like, if some person is there who is suffering from, say, heart disease. Okay, and if that person is given some unwanted drug, then that patient can lose life, his or her life. So that data should be accessed only by authorized person. So this biometric is one of the ways by which we can enhance this security. So insurance fraud, so it is just to, again, to double verify whether the person who is getting the treatment is the same as who is insured. Okay, based on name or father name, maybe there is a there may be a match, but the person may be different, just like the impersonation we have. So insurance is at some other person name, maybe the patient name and that insured person name is same, father name is also same sometimes. Okay, but this can be helpful there. Audit trail, audit trail is like biometrics can also generate audit trail, like some kind of log records can be maintained. Okay, and it may be accessed, like when the person has logged into the system, what data that person has accessed. Okay, these kind of audit trails can also enhance this security and prevent the fraud systems. Now, if this biometrics is there, so instead of getting yourself registered, for example, you have initially enrolled at some hospital. After that, person will come. Okay, person can present his face in front of the camera. Maybe face is one example I'm taking, in front of camera, and all the records are there, just like the ATM machine. So at the like terminal, there are few options that can be exercised by the patient. Like you want to get appointment, click on appointment. Okay, person is identified, everything is ready, just only thing is that the machine will ask what you want to do. Okay, so you want to get appointment, click that and just go to that doctor. Okay, so everything will be ready, no need for the physical document, anything. And you will also be assigned a time slot. Okay, based on that, even this can be done online. Okay, using some online app or online website, so you can be recognized, you can be assigned a time slot, just like we are doing the physical things nowadays. So it also increase the staff efficiency, means lot many people will not be required just for the reception. Okay, or for the assistance. So these systems are so powerful that they can reduce the staff requirements, and staff can use this save time in other works. Okay, and it also reduces the cost. Basically, just I was telling you that instead of there is no requirement of physical printouts. Okay, most of the reports nowadays you can see everything is mostly is online. Okay, so based on this biometrics also we can attach everything at the one place, just like the ERP systems we have. So hospitals also, some hospitals have this ERP systems in place. Everything, patient records are collected at one place, and through the interface they can be accessed. Okay. Now we will discuss more of like the biometric part. So these healthcare applications we have discussed and where they are useful. Okay, in the healthcare part. So now biometric recognition, basically how we can recognize. So recognition is having two components. One is known as the identification. Okay, identification is like if there is some person standing and this person is presented presents his her face or any biometric to the biometric reader. So then there is another component. Uh, this biometric matcher will take this biometric reader input and will try to match who is this person. Okay, okay, who is this person. So then this person will recognize, and this may display, and this data can be used as that this person is maybe Emily is written here. So this identification process is that from this one face, okay, I'm trying to compare this face with n people in the database, and I'm trying to get this match. Who is this person? Okay, this is one scenario that is there, and from where these persons have come in the database during the enrollment phase. Okay, when we are enrolling any person, so we are trying to capture their biometric, and then we are storing that biometric in the database. Okay, now verification is like this person claims that I am this person, I am Emily. So corresponding to this, so biometric reader will check, will capture the input like the facial image, and corresponding to this Emily Dawson, there will be some kind of image enrolled earlier. Okay, then the job of this biometric matcher is to find a match whether these two are same people or not. So you see here, so this process is more of a mathematical one. So now question is that how do you match this facial image with the one stored in the database, and the result will be match or no match. So there will be some threshold. So if their similarity is above certain threshold, then you will say that it is a match, and if it is not, then we will call it as no match. So when I'm saying any threshold, so basically I am talking of the classification problem. So that is all that pattern recognition, machine learning will come into picture. So whether we are able to classify it as a yes or no sample, okay, passed, no, or failed, like that, yes or no. Okay, now this identification is 1 to n. So we are trying to identify the person. Here the verification, just like the online attendance system you might have seen, where you put some kind of ID like the Aadhaar card. Sometimes when you put your Aadhaar card, okay, then you are given an OTP, then you are verified that yes, you are the correct person. Same way we also do it like verification here. Verification is 1 to 1 matching. So 1 to 1 matching is like there will be some kind of performance measures. So you can see this with the help of this 1 to 1 or 1 to n, you can check what can be the how the performance can be measured. Okay, when we have 1 to n, probably the most important performance measure will be the accuracy. So how much accurate it is. So if you are giving 100 people to this biometric reader, and out of that 100 this system is able to match correctly say 70 people, then the accuracy is 70%. Okay, verification involves different parameters like 1 to 1. So false positive, false negative, you might have heard that. So that confusion matrix comes into picture when we are doing more of a verification task. Okay, so like the two class problem that we have. Okay, so this biometric is an application domain basically of the AI, so artificial intelligence. So machine, we are trying to enable the machine with the capability of identifying the person, whether the person is same or not. Okay, so for this you can consider the example of a hospital. So person is coming to hospital, so you are not required to do anything, just present yourself in front of machine. So machine will get all the information that they have in their database with respect to you. Okay, so no need to re-enter again and again everything, and then based on that options that you can move forward. And this applications like for this biometrics, I will just quickly go through this. So these applications can be in banks and airports for surveillance, smart communication devices, personalization for cars and homes. Forensic applications are possible like the criminal investigations. Okay, so that is also part of this healthcare. Whenever there is some murder, so some kind of post-mortem is done, so this biometrics can also help in that case also. So corpus identification, so some dead body is there, then who is this person? Okay, so that is possible if we have like the data of all people, so then we can identify who the person is. Terrorist identification also, parenthood determination is another application where we can have this. Government applications, lot of applications nowadays you see everywhere, like this personal ID documents, border and immigration control, welfare disbursements, we have e-government, e-health. Okay, lot of application nowadays. So this elections nowadays, uh, these are being conducted in the offline mode mostly. That machine is coming here. Okay, so in futures, like most of the countries have started this, so there are online voting. Okay, in India also few private agencies like that IETE or IEI, they are also conducting the elections in an online way. So you are given a membership number. Then there is some kind of online link where you can cast your vote. Okay, you are given an OTP. So based on that OTP, you can just uh, give your vote online only. Okay, without moving here and there. In future, that elections can also be done online. So with the help of AI systems, you can present yourself in front of machine will recognize. Okay, there may be some kind of local enrollment, like we have this voting system. So even that is possible with the help of biometrics. E-health. Okay, so this is the topic for today. So this e-health. So everything we want that healthcare should also be uh, accessible as easily as possible on mobile phone, on internet, okay, on the hospital system. So without having to worry, without carrying the reports, everything is accessible. Okay. So this driver's license, passport control, etc. And the most important application for this is the Aadhaar card. Okay, besides this, you have some commercial applications like the doors, devices. Okay, you can enable them like the biometrics or some fingerprint that can be put in the door itself. So you will be recognized only if the fingerprint is correct, like that. Networks, internet access, credit cards. Means it is not the end. So like as the time is going by, more and more applications of this biometric are possible. Okay. Now, the working principle we will be discussing quickly. So, how does this biometric recognition basically works? Okay, just in a formal way, we have already done this. So, in the initial phase, you enroll in the biometric database. So, you present your biometrics, so that will be captured and processed. So, this process is basically where all that feature extraction, okay, different kinds of feature extraction, deep learning, or any kind of other process, machine learning, all these things are done, and then the data is stored in the database. Okay, so when some person comes for verification, then again the same process will be done, but only comparison will be a new step. So the biometric you have presented, so that will be processed, and the representation will be compared with the one stored in the database. So either it will be match or no match, like that. Okay, now the problem with the biometrics is what? So if I give you an example, say typically, what do you feel if you try to capture the image of your face? So it will be of the order of approximately, say, 500 by 500 pixels approximately. So you can see this 500 by 500. Okay, I'm just taking a tentative figure. Okay, so how many pixels are there in the image? It will be approximately 500 by 500. How much?
Around
2
I
lakh,
asked.
around 2,50,000. So 2,50,000, if that much data is there for one sample, and we have thousands of samples, okay, in the data, because for each person we will have at least few samples, maybe 5 to 10 samples for each person. So if we have 2,50,000 pixels for one person, and if I multiply by 10, so approximately 25 lakh pixels for one person. And if that data is to be developed for, say, one city, so you can imagine that what will be the size of the data. And even if I put very high speed computation, then finding out that uh, person identification of person will be very difficult, or it will take too much of time, that we will not be able to respond to the human query, or we will not be able to identify within a reasonable time, like maybe half second, 1 second, 2 second, maximum 3 second. It will take few minutes. Okay, then this kind of system is not required. Okay. So how can we tackle this? Okay, second thing is small sample size. We cannot have infinite number of samples. So like I have given you one example, like 5 to 10 people are there, 5 to 10 samples are there for each person. So we have very small samples on one hand. If I try to increase, again the size will further increase, so that system will not work. Second way, will have this curse of dimensionality. That is, we have very large dimensionality for one sample. Okay, So how do we deal with this? So this can be dealt with the help of two ways. Okay, one is that I increase the number of samples. I have discussed this, but it will further increase the size. It will further increase the time required for proper identification. Okay, so that is of no use. Okay, second thing is what I can do is instead of this having 2,50,000 dimensionality, I can go for reduction in the dimensionality. So how that reduction in dimensionality is possible? There is a very popular approach in literature. So those who have just started their research, so it's very useful. They should always go through this. There is a very standard approach in almost all the fields. Okay, right? So that approach is the principal component analysis. And now we will be discussing that how this PCA can be used. Okay, so this PCA, principal component analysis, if we are given this kind of data, okay, so very idealistic example I have taken here. So, but it is the crux of this PCA. So if the data is spread like this, and there is some kind of direction in which there is lot of variation, okay, than the other direction, then what can be done is instead of having these two dimension, okay, instead of having these two dimensions, say x1 x2, what I can have, all this data can be represented as a 1D data. Okay, this is easy for visualization, 2D to 1D. But what I told you, that if I have like say 2,50,000, that much of data is there for one person, so can we reduce it to very small dimension like 50 or 100 or 500? So you can see the reduction is more than 99%. So that is possible with the help of this kind of method. So this main idea of PCA is to reduce the dimensionality of the image space, so that we have. So originally we have this dimension like x1 and x2, but PCA objective is to find out some linear combination of this x1 and x2. So this phi 1 x1 x2 means some combination of x1 x2. Phi 2 x1 x2 means some combination of again x1 x2. And these two directions you are seeing here, one is this one, this, and another is this one, phi 1 phi 2. Both these are orthogonal to each other. And if we have 2,50,000, so there will be 2,50,000 dimensions. Okay, like that. So can we reduce? So how we can reduce? So one by one we'll be discussing this step-by-step process. So there is a very popular method, that is the eigenfaces. Okay, it was suggested way back in 1991, but it is still being used. Okay, not in this domain, original domain, but in the cancelable domain also, and in newer domains also. So suppose this each of these, we have facial image like this or any kind of biometric image that we have, and it is a m by n image, just like I have taken example 250 by 250. So this image is converted into a column vector like this mn by 1, so that is one vector. And this is the first sample that we have, this is the second sample we have, and this is the nth sample we have, and all these n samples are arranged in a column order. So the size of this x will be what? So this will be, say if we are saying this dimension as d, so this will be d by n. Okay, now we will find out the covariance matrix. So we will determine the mean vector here, mean of all these samples. Okay, one example, if I am able to see, so suppose this is the training set I'm having this, and this is the sample here. So that from these samples I can find out the mean sample, like this is the mean sample. Okay, this will look like this. So I just place my data on the origin, and then I compute the covariance matrix, should be S here. Okay, should be S, not C, it is S here. So once I have computed this S, after that I formulate a eigenvalue decomposition problem. So this S into EI is equal to lambda I into EI. So what does this mean? That if I have my data like this, okay, if I have my data like this, so I should be able to find out a matrix, okay, like EI I'm having. So this EI, I should be able to find out this EI such that if I operate on this S, if I apply this matrix S on that EI, that is also linearly possible with the help of lambda I only. So this matrix operator will reduce to this lambda operator only. Okay. So as a result, what we will be having is that there will be n eigenvectors. So this I is running from 1 to n. There will be n eigenvectors, and out of those n eigenvectors, I will be having these top k eigenvectors corresponding to top k lambda values. I will also show you one experiment, okay, in MATLAB with the time permits, that how this is computed. And this W matrix is used for transforming the original data. So this W transpose X is means the data, original data that we have, and this is transformed using this W transformation, and then the resultant data that we get as Y. So how, and these different quantities are there. So suppose this is X1, X2, X3, X4 like that, okay, the training set. After that I have computed this mean, so this is my M, okay, and these are the e1, e2, e3, e4 like that eigen vectors that we have, okay. So this is known as the basis. Now now what is happening is, if I have some kind of test sample, probe sample I have, so this is basically represented in terms of these eigenvectors and some coefficients. So these coefficients basically help us in identifying any person, okay. So based on these coefficient we can say whether the person is identity A or identity B or C like that, okay. So these are the eigenvectors corresponding to k dominant eigenbases. Now, so first of all, how do we perform recognition in that case? So if it is a probe phase, each of these eigenvectors are used and these coefficients are determined, just like we had done the transformation. And we add the mean phase, and based on these coefficients, we can find out the closest match, like the Euclidean distance. Okay. Now, same way, earlier we had used the 2D images. Okay. Like the image was converted into 1D samples, but we can also use these 2D images as it is. Okay, so A1 is a 2D image. So each of these of size A by B. I can find out the mean image, and then I can compute the covariance matrix like this. So AI minus A, and I can take the summation over all n images. So then this 2D PCA also, it is we have to find out W which maximizes this. Okay. Now, if we have discussed two fundamental things here, the PCA method and the 2D PCA method. Now there are few more problems with biometrics. So it is permanently associated with the user. It means that you have enrolled into some system, but later if your data is stolen by some other people, then the data can be accessed permanently. Is there any way by which we can secure enrollment process itself? Okay, so instead of storing the original biometric, is there any alternative? So that we will be exploring now. And it can't be reissued if compromised. Means if your biometric data is stolen by someone, then it cannot be reissued. Face cannot be changed, fingerprint cannot be changed. So how do we ensure the accuracy in this kind of a scenario? So in this kind of problem, and privacy and security. So this anonymity is lost. This is also a concern. You are no more anonymous. Every time you will be able to, you will be recognized by the system. Unauthorized access. Okay. So if the biometric is stolen by someone, so fraud can happen because the biometric data is available to other person also. Fake fingerprints can also be determined. So there was some news in few times back that if you are showing your fingerprints, like somebody has captured that photograph, even that photograph with the help of super resolution, we can copy that fingerprint, and those kind of fake fingerprints can be generated. Okay, so you should be aware that you should not present your biometric data everywhere. Okay, so to address all these challenges, so that problem that we are having with the traditional biometrics, so the solution is cancelable biometrics. Okay, so the cancelable biometrics, the our job is to convert this original sample into another kind of encrypted representation that we are having. Okay, so like this facial image is converted into some kind of cancelable template, and this iris image is also converted into some kind of unrecognized pattern. Okay, even if the fake person intruder gets access to this, so nothing is revealed. Okay, no biometric data is revealed. You can see here also. Okay, so your biometric is safe, and in this encrypted domain itself, you can get access to the data that you have. So this is the schematic diagram, that how this encrypted information can be used.
So we can use some kind of transformation features can be extracted from this representation itself, and then matching can be done in the encrypted domain itself. So that is the basically the part of the cancelable biometric that we have. So initially we had the biometric, now we have the cancelable biometric. The word cancelable here, so what does this signify? Even if some intruder has got access to this, we can regenerate this data. Okay, so from the original biometric, this data can be generated multiple times. We will see that how we can modify this PCA by some other method, that is the random permutation. Okay, so this random permutation method, we'll see how we can generate this. So first of all, I explain you what is this random permutation. Random permutation is a kind of concept where you try to use identity matrix. So now if you see, if I have this 1 0 0 0 1 0 here, okay, and this is say 0 0 and say 1 identity matrix. If I apply this on some image here, I take this image as an example, say 1 2 3, okay, so 4 5 6 and say 7 8 9. This is one example, very small example I am taking so that you can, all of you know this. Now if I change this identity matrix, instead of this I just permute its rows. Okay, so I have made them, say first row has become the second row and the second row has become the first row. Now if I apply this on this matrix, so can anyone guess what will happen? So if I take all this matrix here, so what will be the result? So this, if you multiply this and all this matrix, you will find that 4 5 6, so this second row is getting on top and this 1 2 3 will become the central row and this will be 7 8 9. Okay, so if this is a very small example I have taken, but if I want to have very large image like this, and this image is of size, say for example 256 by 256, then this identity matrix will be of size 256 by 256. And if I randomly change these rows or columns, so in that case I can generate this randomized kind of data. So that is the concept of random permutation that we have. So this is the random permutation matrix that we have here. So in this mathematical formulation, now you see, if we are given image xi and I apply this kind of random permutation p, so what I get is another representation, that is zi. Okay, so xi again, as I told you, this is a 1D vector. I apply here random permutation matrix, I get a vector zi. This zi vector can again be converted back into the 2D, just like this we have done here. Okay, so original image converted into 1D, random permutation matrix applied, and then it is converted back to this. So this is the result, that is zi. Now again I will be using the same concept as PCA. So mean vector can be generated as z bar. So that is the mean of all of this. Now this scatter matrix, same way as we had the PCA. So all these components, all these images that we have subtracted by the mean, and then I take the summation of over all images. Okay, so now each of these zi here, so I can just put it pxi, because this zi was equal to pxi, so I am using here pxi. I use then px bar, again I am just putting the values and I solve this. At the end what I get, so I get this matrix in between, which is the same as the PCA. Okay, and it is pre and post multiplied by this p and p transpose respectively, and I get this s1 dash. So using this s1 only, I can get s1 dash if I know this matrix p. No need for transformation of the samples like that. Okay, so this criteria for this are random permutation PCA, same way that we had done earlier. Again we will be able to find out that WPCA. So this WPCA also, for this was P transpose W dash. Okay, so this W dash matrix for the random permutation PCA can be found using this mathematical expression. Okay, so W dash is P multiplied by the WPCA that we had. Now how here we have used only the same kind of transformation for all the samples, but it is not possible. If there are say 1,000 people, I cannot use same random permutation for all the people, because in that case what will happen is, once that random permutation matrix is stolen, or it is compromised, in that case all the people biometric data will be available to the intruder. So what I can do is I can use this PI for individual users, so that I have this transformation individual for different users, and the data of each patient is more secure. Okay, right? So in 2D also the same thing will happen. So here we pre-multiply and post-multiply with this Q and R. So now after that, this is the mathematical formulation, same way we have done. So just like the PCA, but it is in the case of 2D. Okay. So here we are using two matrices instead of one matrix. One for the row, changing the rows, another for changing the columns. And this is the mean, again the same thing that we are doing for 2D PCA. So here we are using this S2 as the scatter matrix or the covariance matrix. And lastly, this is the very similar formulation that we have as we have in the PCA, but the results are a little bit different here. And this W dash, the transformation can be obtained by pre-multiplying by R transpose for this 2D PCA. Okay, I have just skipped this mathematical part. Okay. Now this applicability, again the same thing. Here we are using this individual RI and WI for individual users. So now if we have this training images as only a single image that we have. So this RP-PCA and RP-2D-PCA both are applicable in that single image scenarios also, where we have extreme scarcity of samples. Only one sample is available. In that case also, these methods are applicable. Now I will show you some of the results here, and I will also show you that how we can convert this image, biometric image, into the random permutation way, how we can do it. Okay. So now I now will be showing you some of the results, and then I will be showing you some of the implementation part. Okay. So before I go here, so I can show you some of the implementation part if I have. So all of you can see. Is this visible to everyone?
Yes, sir. Visible to everyone. Visible.
Okay. So like I just take a very popular image here. So cameraman. So you can take any image depending upon the domain on which you are working. So I is the image. I just show this. Okay. So you can see this image, everyone. Now what I do, I can convert this image into 1D. So J is equal to reshape I. Oh, okay. And what should be that? Size of A, size of I. What I can do is 256 into 256 by 1. 256 into 256, because the size of this image is 256 by 256 by 1. So this J will be the, you can see here J is a column vector now. So it is 65,000 like that. So all the intensities of this image have been organized into a single vector here. Now I can generate a random permutation matrix P is equal to rand permute. So this is a function, so that can be used to permute. And what value should I give here? 65,536. Okay. So now you see here, when I have done this P is equal to rand permute, so it has given me some kind of random indices. So it is from 1 to 65,536. So they are randomly permuted here. Now what I will do, based on this I will generate. So it is I is a function which generates the identity matrix, and I have passed here say P. Okay. What it will do, it will generate, and dimensional arrays are not supported. Okay. Just do this 1 by P. Okay. Or P by 1. So this will change all rows by 1. Okay, so first I generate this. Say this is say R. First I generate this of size 65,536. Okay. So now
32 GB. Just I take a smaller example, maybe some, say 500 I take. Okay, I can reshape this size, resize I to size 500 by 500. Resize. Okay. Function. Resize. I am resize. Okay, so it is I am resize. Very good. So what you can do is I am read this say right. Okay, so they are taking resize to 0.5. It is reduced to 128 by 128. So P is equal to rand per mute. Again, I am taking say 128. Because of larger size, it was not able to do rand per mute. Yes. Now, based on this, I generate say a identity matrix which is of size say 128. Is 128. Now, this P is there. This P you can see here. So it is having indices which are different. Okay. They are all marked up to 128 in different ways. Okay. Now, I just write here. So R is equal to R, and these rows I want to change. So this P is equal to this. I want to access this R in this way. Okay. Now you see this R has changed. Earlier it was the identity matrix, but now it has changed all rows and columns. It is all 128 by 128. One, 128, and R is equal to R this P comma 1. Is of size 128. This R is I just see this one R1 P comma 1 comma P is 128. There are some issues here that I'm not able to do this, but this way given this image, what we can do is we can convert this into a 1D image. Suppose I just convert this I is equal to I suppose I have read, and I generate IR is equal to rand. I am directly applying this. Okay, so random permute 128 is 256. Okay, so now I generate another image using this R. So R as the rows, okay, and R as the columns. Now if you see this J and I just show this. Figure. Figure. I'm just showing you this J. Huh? What is happening here? Acha. Figure I am show. You see this one.
The figure comma I am show. Figure comma I am show. Figure comma 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 comma.
Now you can see here.
Okay.
Now you can see here that this original figure that I had, that was of cameraman. Now I have simply, what I have done here is, I have read one image initially here, the cameraman image. Then I have generated this R using this random permutation. So 256, like 1 to 256 random values will be generated, and using this image, using this equation J is equal to I R means randomly I have selected the rows and randomly I have selected the columns. So rows and columns I have selected. When you see this R and R, I have used this original image I for selection, and when I use this I am show, you can see here how it is shown. Now if I use another figure here and I show you the original image also, then you can see both the images, that how this random permutation can work. Okay, so this data of this image and this image both are same. So can anyone tell whether they are same or not, but just by seeing?
By looking, it is not same, but content wise it is same.
Yes, content wise it is same, so that visually nobody will be able to tell. So if I just find the mean, okay, mean of this I, if you see the original image, so that you are seeing this, and mean of this J also, you will be finding that this is also the same data is there. Just by random permutation I am able to change the representation here. So the same thing we are doing here in this research work also. So this we had tried this approach on 3 different data sets here. So the ORL, that is having the 40 identities, data of 40 people, UBRIS having the 241 identities, and the IIT Delhi having 125 identities, and the total images are given here. And these are the some of the sample images that we have. For first one is the ORL, then the UBRIS, IRIS, and the third one is the year. So we have tested this on 3 different biometrics, this approach. And this is the cryptic patterns that we have got using this approach. So the last two ones, this is the random permutation PCA, and this is the random permutation 2D PCA. There were some approaches available in literature. Okay, so this first one was the gray combo, then this is the gray salt. So it actually increases or decreases some kind of salting method in the biometric images. And this third one was the block remapping, like this image was partitioned in terms of blocks, and these blocks are rearranged just like we have done individual pixels. So these blocks were rearranged, like you can see here, somewhere we are able to see the eye, okay, somewhere we are able to see the hair, like that. So there was glimpses of the facial image, or some kind of data still can be guessed which kind of image it is. Here salting also, it shows some kind of facial image. You can see here some eyes are visible, some lips here also the same thing. It is something like hazing kind of thing, but here you see no kind of traces are there in the random permutation PCA method. And in this 2D PCA also same thing is happening. For different biometrics we had the same results here. Sorry. Then this for the ear images, very similar results, and these are some of the results that we have got on different databases with different training images. Like when we use this approach for only 2 images per person, okay, very less number of images,
still we got very good high accuracy with the help of random permutation 2D PCA. Okay, for 1D PCA, like the accuracy was increasing as we increase the number of principal components. Okay, so when we increase it to 20 components, so this random permutation PCA and 2D PCA both were very good. Okay, and for other approaches we had seen that the approach were not that good. Okay, so when we increased the training person from 3, 4, 5, we were able to achieve accuracy of approximately 94% here. Okay, when the training images are increased, but with only 2 images, still the accuracy was more than 80% here. So for the iris dataset also very similar kind of observations were there, but the proposed approaches, they outperformed all the previous methods. Okay, now this is the classification accuracy for years dataset. After that, we had also done some kind of computation time, how much time is required by the two methods. Okay, so you can see here the training time that is required for RP-PCA was larger. Okay, because each of the images was converted to 1D vector, but here it was converted only to 2D vector. There was no conversion required, so time required was very less. Okay, so 0.39 seconds when the 3 images. So as we increase the number of images here, so the training time requirement was more and more. Okay, and for similarly for different data sets we have this training time. Now it is important that we also do the security analysis, how much secure the method is. And if I want to track that how much secure that method is, so I should be able to check that how much time it will require to break that code, so break that pattern, so that we have. So if we assume there is no prior knowledge of anything, any pattern, and I consider this ORL image which is of size 112 by 92. So for this we have 112 by 92. So this was the size of the image when it is converted into 1D vector. So this is 10,304. So this kind of image when it is converted into a vector, and this is pre-multiplied with a matrix of size 10,304 by 10,304, just like I have shown you that random permutation matrix. So determining the entries of this random permutation matrix, so will require how many arrangements? 10,304 factorial. So that many arrangements, and that actually if I write this factorial in terms of 10 raised to power, so it is 10 raised to power 36,878. Okay, very large. So what I have done here is, so I have done some computation. So if I use this brute force attack just for breaking this system, so how much time I will require? That many years I will be required approximately. Okay, for similarly for UBRIS we have this, and IIT Delhi this is for 1D, so that many years. Okay, 10 raised power 2 is equal to 100 years. Okay, more than the lifetime, average lifetime of a human being. So it is like 10 raised power 31,000. Very large amount of time is required if we are analyzing this in terms of brute force. Similarly, this RP 2D PCA. So 2D PCA requires two matrices. One was for the pre-multiplication and another was for the post-multiplication, if you remember. So if the image is of size, say 112 by 92 here, so it will be 92 by 92, and it will be 112 by 112. So the left side matrix will require that many arrangements, right side will require that many arrangements, and this multiplication will be equal to 10 to the power 326. So if we analyze all this data, so that is actually I'm taking the fastest computer multiplied by number of seconds and 365 days in a year. So how much time will it take for breaking that? How many years it will take? 10 to the power 17 I have taken here also. The fastest supercomputer available today, whose speed is in petaflops. Okay, we have the normal system which are of the order of gigahertz, but these are the petaflops if I take, and you can see here still the number of years required to break out this is very large. So not easy to break using the brute force attack. So this was one of the publications in applied intelligence. It was a little old, so 2018, but still it has been used in a lot of many applications. Okay, now Finally, I conclude this. So like this security and privacy concerns we have discussed with the biometrics. Then we discussed about the healthcare applications of this. We have also discussed the random permutation PCA and random permutation 2D PCA. And finally, we have seen that the performance of both these methods are better than the other several state of the art method, like the block remapping is there, gray salt is there, okay, like that. So gray combo is there. So security analysis in terms of number of years for this brute force attack we have also seen, and we have seen that this is a very secure approach. Okay, so if you have any queries, then you can ask.
Participants, if you are having any query, you may directly ask.
I hope I'm able to make your last 1 hour useful. So at least you have learned something new.
Yes, sir. Surely it was very helpful. And you have explained the PCA with the biometrics, and that was a new topic. And you have covered the machine learning concept also. And even you have taken the lab session also. So that is very much useful. So on behalf of all the participants, I just want to thank you. And I think one query is available that earlier back, the Smriti Misra is asking, sir, it is possible to learn blood profiles or blood components details or at least blood group using fingerprints. Fingerprint, I think ये fingerprint होगा. As per my knowledge, it cannot be done using this study. Please explain this scenario, or else what other options can be apart from DNA and lab testing as biometrics. So actually, she want to know something like blood profile can be used as a biometrics, or like what is the research in that, or what is can be the like. Can you explore this one? Can you say
Yes,
something about
I
it?
think directly it is not yet possible, but like blood group is something which is inside the body, and these biometrics are working like most of the biometrics work for a distance when we are want to work at a distance. Okay, so no doubt there may be some scanning systems which may be like the radar we have, or which can go through inside the body, just like your MRI images are there. So they may be able to better apply this on this, but not the PCA or this 2D PCA.
Okay, thank you, sir. Thank you for presenting your work. Thank you. Thank you very much.
Thank you, sir. Thank you.
So participants, now there is a break of 10 to 15 minutes. So will be joining after 10 or 15 minutes. And I will be taking the next lecture because Dr. Bala Chakwati Nilapu shall not be available today. He will be taking tomorrow's lecture. Right. So after 10 to 15 minutes, we will start the next session.
Sir, good morning. Kindly share the material, sir. It will be better for studying. Thank you.
Videos I will share. Can you able to see the recording in the chat box? Mr. Sukumar Devnath, can you able to see the recording in the chat box?
Yes, sir.
Okay.
That
Yeah.
10 recording has started. That one.
No. Stored recording is available there. Okay, maybe that not
No,
with
sir.
that is
No, sir. No, sir.
okay. That is not visible
Yesterday,
to participant. I think
16:51
actually
hours is there for recording.
Yeah. Any material,
okay.
sir. No problem.
Okay, then I will actually that has been compiled and in the chat
Yeah, right,
in my
sir. You
chat box.
compile and then, yeah. As per your
I
convenience,
will
sir. No
compile
problem.
and then will send to all the
Thank you.
participants.
Thank you.
Right.
Thank you, sir. Thank
Okay.
you very much.
Okay, good afternoon, candidates. So I hope my PPT is visible to you.
Yeah.
In on full slide mode, I think so. Okay, I hope just wait for another minute if anyone else is also joined because currently only 22 candidates are there. So let's wait another minute if the others are also joining. Okay, now we start. So the title of my talk is Three-Dimensional Anatomical Surface Prediction from X-ray Images for Computer Diagnostic. So this is a research work which is done by one of my student, Miss Payal McCain. She completed her PhD on this topic, or in fact, I'm showing her work only. This work is a little bit innovative, where we have tried to develop the three-dimensional volumetric or three-dimensional surface image using X-ray images. Like we are able to, like we have used X-ray image only, that is a 2D image, and we are able to make the 3D surface image. Like in short, you can say like 2D to 3D. However, by just looking at it, it seems to be very like unrealistic or impossible kind of thing. But for particular application or for a small module, we can do it. And in fact, in the literature, the people have also done it. So we'll see like general phenomena or general steps. Like if you are targeting of doing such kind of experiment, so what can be the general steps or and how we have done it. So we'll show that one. So in brief, what I will be explaining. So like here you see two X-ray images. One is the lateral image, or you can say the side image, and another is a PA image, posterior anterior image, which we call it the front view of image. So two images are there. Here seems like this is a volumetric or three-dimensional knee, and this is a projection of knee from the front side, and this is the projection of knee of from the side view or from the like lateral view. So the reverse engineering is like what generally happened is this is a three-dimensional body or three-dimensional object. Generally, we used to take the X-ray image of three-dimensional image from the front view and from the lateral view. But here, what we are trying, if we have two side views like front, one side view and another is a front view, two views, two projected views, and then we are able to make the 3D view, right? So similarly, you can see the other body part also. We are using the two images, one side view and another is a front view. If we can make the three-dimensional anatomical surface, here also you can see the two images, and using this 3D is developed. So the basic idea is if we are having the X-ray images, either it is a one or two, or sometimes more than two, then using those images can we make a 3D surface image. Here I am saying repeatedly I will be using sometimes 3D surface image and sometimes 3D volumetric image. So can anyone say like what is the difference between both 3D surface and 3D volumetric image? Anyone can say or have idea like what is the difference between surface image and what is the difference between like what is the difference between surface and volumetric image? Hmm?
So image. Hello.
Yeah, yeah, please.
Yes, sir. So surface image is regarding the two D only, and volumetric is about the 3D. It takes the all the three dimensions into account.
Okay, right. So here I am saying 3D surface image. So basically, I want to say that like if this is a 3D volume, then only if I will be talking about only the surface one, not going inside, then this will be the 3D surface image. But when we saying the 3D volume, it means we can traverse any of the internal coordinate in any of the three-dimensional coordinate and can see what is the value. But in case of 3D surface, we are concerning about the surface only. We are not concerning about inside the body. Like like this is a knee, we can see the surface and we are concerning about the surface only, then this is a 3D surface. However, we are not concerning this is a hollow or this is a like having some density. We are not concerning it in the 3D surface only. But in the case of volumetric image, we are concerning about the inside the body. Like what can be the intensity value, what can be the like that is a diluted knee or that having some disease inside the knee. So we are not concerning in that 3D surface, but concerning in volumetric image. So this is a basic difference of 3D surface and 3D like volumetric image. So here, that's why I am using 3D surface image when we are creating the 3D volume or when we are creating a 3D surface or 3D from two images, then I will be using 3D surface image because I will be concerning about the contours or like surface one, not concerning more about inside the body. Right. So now, so in the talk, I will be discussing the computational tomography, then human upper airway as this experiment or this analysis on the human upper airway. So we'll be talking about that. Then significance of the problem, then a few literature methods, then general steps which can be used for 3D surface prediction from two-dimensional X-ray images. Then we'll take two case studies. One is the one case study on femur model reconstruction from biplane or like two X-ray images that is done by IIT Bombay. So I will be including this one. And another case study will be based on my PhD student work, where 3D surface reconstruction of prediction of maxillary sinus from two X-ray like lateral and PA. Then we'll discuss some challenges of 2D to 3D reconstruction technique. And after that, if time persists, then we'll discuss a systematic review, which we have completed on this type of work only. So we'll see if time permit, then we will discuss the systematic review and then conclude. So first, we will discuss a little bit about the computational tomography, the audience or the participants who are not aware about the CT. So that's why I kept a little bit introduction about the CT and MRI. So CT, you can see in the image, this is the CT machine. The CT machines are there with the different manufacturer like iCat scanner and many all. So like full form computational tomography, it gives the three-dimensional it gives the three-dimensional output, like give the volumetric image. You can see inside the body also. You can traverse any of the coordinate of the body and can see what is inside that or can see the details. However, that is a like reconstructed image. That is not. We are using the image like in the if you if you will be referring the first session, then Dr. Dinesh Kumar, Professor Dinesh Kumar was referring this one. That is not an image, but that is a constructed interpretation. You can say because the image is not in the visible spectrum. So here the CT image. this CT scanner will be giving the uh, three-dimensional volumetric view. However, as we receive from the from the imaging from the imaging 2D in the form of 2D slices, and then those slices are stacked and made the 3D object. In this machine, we can see this is a bed where the patient lies. Here you can see this is a black one. This is a a setup where the head of the patient or head of the person can be stabilized and can go inside this body, and inside the body the X-ray source and detector both are there, and they used to rotate and then the imaging creates. So if conceptualize, if we see on basis of conception, so basically the concept is similar to the X-ray. Like one X-ray source is there, and this is the body, and here the detector is there. So if X-ray is incident one time only, then on the detector side, you get one image. So this is a X-ray image. But if we take the multiple X-ray by rotating the X-ray source as well as the detector, and the keeping this distance same, we rotate this assembly. Actually, in this CT scanner, in this box, majorly the X-ray source and detector are there. So if we rotate this assembly multiple times, so we'll get the multiple images of the same portion. So by solving them multiple like using simultaneous equation, we can get the value. So we use the equation like this like Ni is the input intensity of X-ray, N naught is the output intensity of the X-ray, and mu is the linear X-ray attenuation. Basically, the mu is the one which we call like Hounsfield value in case of CT. So this is a special coefficient of the body. Here we kept it one, only the one coefficient. It can be the multiple also. Like in this case, there are multiple different intensity value can be there, or multiple particles can be there. So each particle or each item will be having the different mu value or different attenuation. So the series of coefficient can be there. So roughly, if we keep the or establish a relationship between those, so that can be like n naught equals to ni into e power minus mu uh, delta x. Here delta x is the distance between the source and detector. However, we have to keep this distance same. If we are changing, then this delta x will be changing. So this establishes the relationship and gives the value of mu. In case of 3 mu, then this will be equation like this. So there will be like for one incident, this will be one equation, and after rotation, there will be multiple similar type of equations. So in that way, I just making it visible to you, like how the CT is reconstructed, or CT values or the Hounsfield values are defined. So in one rotation, there are multiple equations where multiple mu's are same. So we can solve them and can get the value of mu. Mu is just representing the Hounsfield value, which we see in case of the CT slices. Here, this one rotation will be completed in multiple X-ray incident. So this will give the imaging of only this cross-sectional part. So if we want the the imaging for the other cross-sectional part also, then the motorized table move down, move up or down. Then again rotation is there. Then again motorized table will be moving. Then again rotation will be there. So there are multiple rotations and multiple movement of this table. So in one rotation of X-ray source and detector, one slice is created after motorizing table, another rotation, another slice is created. So in this way, there will be the multiple rotations and multiple slices will be created. However, we have to see that that so many times X-ray incident is there or X-ray like X-ray exposure is there. So this will be harmful for the body. This is a like very harmful for the patient. So we'll discuss about that one also. Here another terminology also comes into the picture. The CBCT, cone beam computer tomography. The output seems to be very similar to the CT, but here the difference between CT and CBCT is the CBCT will be taking the less amount of radiation. Why? Because in case of fan beam CT or the conventional CT, the source is the source from the source X-ray exposure is there, and on the detector only 1D scanner is there or 1D detector is there. You see, so at one rotation, only one slice or one cross-section parts are observed. But in case of cone beam computer tomography, our detector is two-dimensional detector where source X-ray will be radiating in the shape of cone. So that's why name is cone. So at one rotation only, the complete imaging is completed. Like complete body is like complete body is observed at the detector. So due to this difference, the name as the cone beam. So this is a cone beam computer tomography data, and here the CT computer tomography, like in one incident, the 1D detector is there. So multiple rotation will give you the multiple slices, but in this case, only one rotation will give you the image. So that's why the radiation amount of radiation is also reduced in case of CBCT. So if we talk about uh, image acquisition, so this X-ray source and the human body or any like the CT is not only the human body, like you can do the CT of any other body also, animal or anything you can do. The CT like detector will be detecting, then you will be generating the number of 2D slices, and those are stacked, and when you stack all of them, then the volumetric view can be there, or you can visualize the 3D in the 3D form. Here, this visualization is not the surface visualization. You can go inside the body. You can see the intensity value or the voxel value at every coordinate, every 3D geometry. You can go inside, but the problem is you need to have the sufficient amount of software or sufficient facility of the software which allow you to go inside the body and can visualize the particular organ or particular like a particular pathology. So, CT visualization, this generally we do like this. Here, when you get this, like from the CT scanner, you get the 2D stack slices. And if we see in any software or any CT, like CT compatible software, this is just a snapshot of Mimic software where you can see this slice is the axial slice, like from the top view. If we see all the slices from the top view, then you will be looking like this. This is a 3D volume rendered image, like how it look like from the outside. This is this imaging from the side view, and this is from the front view. Right. So for visualization of one data or one human data or one CT data, this type of software is required where three different cross-sectional views are there and one volumetric rendered view is there. Like this is a 3D slicer view, not mix. This is a 3D slicer view. And generally, in the CT image, Hounsfield values are there where air content are defined around -1000. If fat is there, body fat is there, so that is around -122, -90. Soft tissues like 100 to 300. Some bone, like bone are the hard tissues, so that's why 300 to 400. You can see this white portion. This is the bony portion, and this is hard portion, so that's why the image intensity is higher. And cortical bone, that is the highest quality of bone, so the intensity is from 500 to 1900. The higher the number is giving you idea like that is a hard amount, like a hard portion, or a very strengthened portion. So here we'll see somebody want to say anything, or let me. Okay. So you can see this video over here. I think you will be able to see the video. Just second. Yes. So now this is a 3D volume rendered image, and here this like he just let me pause it. This is a cross-sectional view. Here, this is a button to scroll. So if I will scroll here, then you will be able to see the multiple axial images in reference to the 3D volumetric image. So see over here, when I am scrolling this one, you can see this plane is also scrolling, and correspondingly we can visualize the views. Similarly here, that is a frontal view, or coronal view, and this is a sagittal view, side view. We can scroll every type of slice from here, and correspondingly we can correlate with the 3D volumetric view. This is a snapshot of mimic software which can be used for the analysis purpose of 3D volumetric images. Even you can rotate this 3D volumetric view. We can see over here, and if we want to annotate, like you see over here the process, we here we will be plotting one landmark or annotation. Like you see over here, we have plot one landmark. So here we can scroll the slices and confirm the location of the landmark. So one Pogonian point has been marked. So in cephalometry, there are multiple landmarks, cephalometric landmarks are there, which can be plotted using this software, or any annotation which a radiologist or a expert or a person who is analyzing the image can do the same. But here showing this one, the idea of showing this one is to demonstrate the complexity of the three-dimensional data, like how complex it is if we are doing it manually, because we have to traverse each and every plane, then we have to annotate, or any measurement is required, then also it will require to scroll the multiple slices in coronal, sagittal, and axial all, and even we have to confirm it on the 3D volumetric view. So this is just giving you an idea, and you can see the human geometry, anatomical geometry, that is not regular geometry, that is a very um, uh, like uh, very irregular geometry. So here this one. So now we go next. So if we compare CT and MRI, so by visualization, it looks like the CT computational tomography looks like this one, where the the bony portion is prominent, and soft tissue, the different soft tissue are not prominent. They look like of similar intensity levels. If the radiologist or if a doctor is more concerned about the bony portion or the hard tissue, then probably he or she will be recommending the computational tomography, where the analysis on the bone can be easy. But in case of MRI over here, if the analysis is based on the soft tissue, where the different soft tissue existing, they want to visualize them, or they want to see the see any tumor or anything, so the MRI can be recommended. So MRI look like this one. So the sometimes the student confuse like what is CT and what is MRI, and how, then sometimes they feel like these are same, but actually these are very different. However, both the data are of three-dimensional anatomical data, but the visualization of both the data is very different, and the applications of both the data are very applications are both the data different. But here I am putting both the things to explain you, like the MRI is free of any radiation. MRI do not involve any radiation exposure. MRI is based on the magnetic resonance, and CT is computational tomography based on X-ray. So CT equation can be dangerous to the patient because the radiations are involved. But in case of MRI, the radiation wise, it is free of radiation, so that is not dangerous. But other issues like it takes some time, costly, and many other things are there. But mostly radiation is very important. Like radiation wise, the CT is very expensive. So if we compare the CT image or X-ray image, like X-ray images or the different variation of the X-ray based on the radiation. So this is just this table is taken from one of the article. So roughly we can say like if chest X-ray is taking around zero point 0.1 millisievert, and abdominal pelvis CT is taking around 7.7 millisievert. So like it is around 77 times. So you can have it like if the patient has taken, if one CT is acquired of one patient, so that is taking around 70 X-rays or 80 X-rays, right? So at one time you have taken 70 80 X-rays, so that much amount of expensive this one in terms of radiation, right? In terms of CVCT like a little bit less, like CVCT you can say around 20 to 30 like X-ray you can say, right? So the similar amount of radiations you take it from the background, like for chest X-ray, like equivalent radiation taken from the background is in the 10 days. But in case of CVCT or in case of CT, that takes the radiation background, or like background radiation is around taken in 2.6 years, right? So here to say that the computational tomography is highly expensive in terms of radiation, right? So this is our objective, like if we can avoid of taking CT for certain task and can provide the 3D surface imaging for having the similar diagnostic value. So, if we compare them, the CT provide the three-dimensional volumetric visualization for human anatomy, and required several anatomical deform. Like in case of some deformed cases are there, then we have to conduct the CT, and very useful for asymmetric anatomical geometry. But the drawback of CT is it is very costly imaging, rarely available. Like at the district level, maybe 2 or 3 imaging centers are there, where you can conduct the CT, where a CT can be acquired. And the important is it exposes with the higher radiations, and it is also like sensitive to the body movement, because at the time of CT acquisition, if body is moving, then the imaging can be repeated. Similarly, in case of X-ray, the X-ray benefit is like it is easily available, very low radiation exposure, low cost, and the image acquisition time is also very less. But the drawback of X-ray, it gives only the projected measurements, like projected visualization is there, or projected measurements are there, and provide the nonlinear magnification. Superimposition of anatomical structures make difficulty to interpret the X-ray images, and problem comes with the calibration also. Like if we get the X-ray, then is a magnified one, so the calibration is also required. So here the idea is X-ray has some drawbacks, and the CT has some drawbacks and some benefit also. So by having that objective, we are trying to avoid the drawbacks of both the imaging and want to use the benefit of both the imaging, right? Meaning to say that we will be using the X-ray by drawbacking the uh, we will be using the X-ray by drawbacking the CT, and uh, will provide the facility as the CT. So we'll see it. So just a domain knowledge type, like in the human upper airway, like many sinuses are there. So these sinuses are important uh, for the the measurement of these sinuses are important for the diagnosis and treatment planning also. Like many sinuses, maxillary sinus, ethmoidal sinus, frontal sinus, right? If we visualize those sinuses using the CT images, you can see these are the cross-sectional area. This is a mid-sagittal view where you can see the nasopharynx, oropharynx, hypopharynx, sphenoidal sinus, nasoethmoidal, maxillary sinus. So there are many different volumes of the human upper airway. The exact volume of these sinuses and this portion is required for the diagnosis and treatment planning. And like if you have heard about like sleep apnea kind of disease, where the diagnosis of this disease is very easy when a CT is acquired, and the volume is monitored, or like volume is captured, like how much volume, like volume is changing or reducing. So so many applications are there. This is a 3D visualization of the volume, human airway volume. You can see over here. Like maxillary, if I talk about the particular maxillary sinus volumes, and then it has many significance. Like sometimes some polyp or some cyst are there. So in those cases, to estimate the volume of maxillary sinus is important. Some chronic sinusitis or tumor fractures or sleep apnea disease. So for those kind of disease, this maxillary volume of maxillary sinus is required to be estimated, right? So that's why our work will be based on the maxillary sinus. So before discussing that one, before discussing this one, we will be discussing some literature, like what kind of similar experiment are there in the literature. So in the literature, we found some experiment based on knee bone or femur bone or pelvis bone or lower limb, where they have tried to make the 3D surface image using the X-ray images. Sometimes the researchers have taken only the one X-ray, and sometimes two X-ray has been taken, and then they have tried to create the 3D surface image. Right, so here you can see some examples where 28 pairs of X-ray images were taken, 30 samples were taken in the case of femur bone, and the lower limb also like 907 cases were taken. This experiment, they have taken 10 samples from the cadaver and many more. So here just giving you the idea, like this work is at the initial stage where people or researchers are doing it for the different organs or the different body part. These are other examples in the same line. Uh, like mostly work is done on the femur and pelvis bone, and on the spine also work is also like work is also there, right? So now we will discuss some general steps for 3D surface prediction from 2D X-ray images. So these steps or these general steps we have created based on the analysis over the literature. So we'll discuss each and every step one by one. So first step is image acquisition requirement. Uh, so for reconstruction, the image is required, like X-ray image is required. Either it can be the lateral and PA X-ray image, or only lateral. Actually, if you experiment which has derived the 3D surface image using the lateral image only. But the problem is, if you will take only the one image, then the other information which is available at the frontal view or the PA view, which will not be able to incorporate in the 3D model. So that's why it is not recommended to use the only one image. At least two images has to be there. If more number of images are there, then that's good. But the another challenge will also come to incorporate all those information in the 3D volume or the 3D surface image. And while image acquisition, patient will not move so that the static information can be taken. Otherwise, the re-imaging can be there. So in the image acquisition, only two images are required. Yeah, Shireen, you want to say something? You have hands. You have raised your hand. Okay, I think that was a mistake. Okay. So next step is the calibration of lateral and PX image. This step is important for the measurement. Like when you will be developing a 3D volume or 3D surface, then obviously you will require to compute the volume, amount of volume, like quantitative view. So if you want quantitative view, if you want to measure them, then you have to do the calibration, because if you will not be calibrating, then there will be there will be problem with that scale or the measurement. So here problem arises when both the images are coming or the source is different. Like both the images are coming from the different sources, so the different scale can be there, different magnification level can be there. So if that type of thing is there, then uh, you cannot use them directly. So you have to calibrate them. Anyhow, if you are using the X-ray image, so X-ray image is the magnified view. So without calibration, if you are using, then there will be a serious problem of the measurement. Right. So to eliminate the magnification between the images or to put both the images at the similar scale or at the same scale, the calibration is required. Then the third step is the image enhancement or the intensity normalization. So image enhancement operations can be performed to reduce some noise or removal of the noise, or if you think like some illumination variation is there, then you can perform the image intensity normalization. Like you can do image histogram matching or histogram equalization or contrast stretching. So that can remove some problem with that illumination condition. But recommended to not use much image enhancement techniques, because if you will be using higher image enhancement or much image enhancement, then you will be losing some actual information. So there is a trade-off of the image enhancement and the information available, because higher enhancement can eliminate the information over the image. Fourth is the contour extraction of the anatomical geometry. Uh, so after that, like in that complete image, you will be targeting any special area or special organ. So we have to extract the contour, or we have to crop that particular region. So for extracting contours, you can use the threshold based method or region based method, edge detection method, or active contour method. The particular method can be applied based on your defined organ, like what type of organ you will be using. But this is a very important step, because if the contours are not extracted exactly, or contour extraction is problematic, or contour extraction are not accurate, then your model will also not be accurate, because after taking the contours, we will be using the contours only. We will leave the original image. So if there is any problem with that contour extraction, or contour has been left somewhere, or that not accurate, then the model will not be accurate. So this is very critical step. However, in our experiment, we have kept this step manual, because our experiment was the first experiment. So we kept it manual, so that we can get the higher accuracy as a first experiment. Then we have to create the lateral and P image correspondence, because we have to create the correspondence, or like you can say, like we have to match them, or we have to create the similarity between them, so that we can align them
Sir,
with
there is
the
no audio, no sound is there.
just a minute. Others are also facing the same issue.
No, sir, we are getting audio.
Okay, so I think if you are not getting audio, then you have to check your system, because others are getting the audio. Or if you are not getting, then
It is not audible, sir.
Sukumar, other participants are getting the audio. You have to check from your system. I'm taking from the till then yeah, from the comment it's saying it's
Not
audible.
audible, sir.
Sukumar, you have to restart your system, or you have to connect again, because other participants are getting audio. Let me write it. Uh, Okay, I think he will see the system. Okay, now we go forward. So for the lateral and PA image, let me make it full screen. Okay. So we have to create the correspondence from the lateral and PA image because we have to combine the information of both the images in the 3D template. So what we will take? We will take a 3D template and we will transfer that information which is available in the lateral and PA image. We will transfer that information to the 3D template and we'll try to make that template as uh, the predicted volume. So before that, we have to create the correspondence between both the images. And that correspondence can be created if you have calibrated them, if you have scaled them, if you have rotated them well. So if that aligned, like just like a alignment. Then we have to do the 2D to 3D image registration. 2D to 3D image registration is like we will be taking one 3D template. That 3D template can be a statistical template and will register the 2D image to the 3D image so that the information on the 2D X-ray image can be transferred to the 3D image. So it is similar like if like we are having two X-ray images, lateral and PA, and where the patient specific information is there, and if that patient specific information can be transferred to the similar 3D template, then that 3D template will be derived into a 3D model or 3D predicted model, right? And then shape will be deformed. Shape deformation is like fine tuning in that model or in that surface image so that it can be it can be cross check, or like you can say like whatever shape has been derived, we are taking it and creating a projected X-ray, lateral and PA, both the X-ray, and we are comparing the our patient X-ray are the same or not. So those were some steps like normal steps or like general steps which can be used to create the 3D volume. So now some methods are there in the literature. We are just seeing some methods like deep learning based methods are there which were performed to create the 3D surface image for the knee bone, for the femur bone, or for like lower limb, right? Some statistical model, like statistical shape model type of methods were taken, methods were used for developing the pelvis bone or distal femur. Like, and the advantage of this statistical shape model was like it uses the prior knowledge of that particular organ, so it gives some higher confidence or like a higher accuracy level because uh, that statistical model has already that information. We have also used some statistical shape model in our experiment. Point based method, like it create a point cloud, and those kind of methods were used in the same like femur bone and pelvis bone. And the other method like parametric based method and contour based method, those methods are also used in the literature. And deformation based model, intensity based model were also used. Okay, so now we come to the case study. First case study, that is the 3D femur model reconstruction from biplane X-ray image. So this case study done by IIT Bombay, I am referring that case study. They have created a small like a small tool that is based on only one X-ray. Like if you can input one femur bone, and then you have manually you have to trace the contour over here, and after tracing the contour, it shows you the 3D surface image. It is not a volumetric image, that is just a surface image, like you can see the surfaces, this one, right? So the algorithm wise, or like the method wise, if we go, then they are able to take the anterior, posterior, and the sagittal or the medial view, and one statistical template model of that femur bone they have taken, and then they have done some initial alignment. However, they have not explained the calibration at all, so that's why it is doubtful for taking the measurement over there. But initial alignment they have done, and then created the correspondence, and then they have created the deformation. So basically, two X-ray were taken, and then some alignment and correspondence, then deformation. So if you will see over here, like this is a projected view, or like projected X-ray over here, or see over here, like this blue line, blue dots. These are the template projection contour. Like this is a template, and this is Salahoti, or you can say like contours, you can say. So this contour, if we project those contours over the plane, then the projected contours in blue look like this, but actually input contours are in black, right? So here the problem is, if we can deform this template in such a way that the projection of this uh, template matches with this black contours, right? I'm saying it again. The problem is that if we deform this 3D template in such a way that the projection of this 3D template, like this projection, will be matching to this black or like input contours. If we can able to do that, then it means we are able to transfer the information of this input contour to the 3D template. So this is done in only one view, like this the frontal view, right? So so the information will be transferred in the one view only, right? So here this is the second view, like this is about to derive over there, and this process has been shown over here, and after that this is complete change, like this is red one. So the change has been made in such a way, like the projection of this 3D template is match with that black or like input contour, right? And now then like this received 3D template is the prediction of, or prediction of 3D surface of femur bone, right? So this type of experiment they have done. So now we come to our experiment, like that is a 3D surface reconstruction of prediction of maxillary sinus from PA and lateral X-ray images. Here, this is the methodology. Here the objective is we will be taking two X-ray images, not one. We are taking two X-ray. One is the lateral like side view, and another one is the PA like frontal view, right? And the output, we will be creating the 3D maxillary sinus volume or 3D maxillary surface image of human upper airway. So we'll discuss one by one. First of all, the calibration. The calibration is a major issue. In lateral, we use the same calibration method which orthodontics do. So orthodontics used to plot a a few landmark on the known distance. So that is helpful for the calibration of this image. But on the PA image, there is a no known scale. So that is a like a challenge of calibration. So we have created one method, and if you are interested in that method, I have published one article on that method, that how to calibrate this posterior anterior image. What we do, if these two images are of same patient, so if we plot two landmarks on the vertical scale, like we plot this Manton and Pogonian, or sorry, this Nagian and Manton, or Nagian and Pogonian. So any two landmark here and there also on the same lateral and PA. So if both the images are of the same patient, then the distance of those points will be the same. So we have equated those distances and then calibrate the image. So this is just a basic idea like how to calibrate the posterior anterior image. So once both the images are calibrated, this is the procedure, or like algorithmic wise, I have included this one, and this is also available in that article. You can read that article here. Just plotting two landmarks and on the vertical scale that are sufficient to calibrate the another image. The second step is the contour extraction. uh, as I already mentioned, that this is a very important step of the contour extraction, because if the extraction of contour is not proper, or any mistake is there, or any deformity is there, then our prediction will not be accurate. So for the uh, like uh, for the first time, we have use this step as the manual step. We have asked the orthodontist to extract the contours. We have taken the data from Ames Batinda, and they are our collaborator, and they have given the data, and they have also marked the contours over the X-ray image as well as the CT image. So these contours has been marked on the X-ray images, and then the contours has been extracted. Then translation. Translation is just considering the 3D template model in point cloud format. This is just an intermediate step, and that is required for the like uh, predefined template model that is requiring for the alignment of the extracted X-ray contour. So we have done that translation. You can see this translation is the changing of the reference frame, because in 3D coordinate geometry, if you are taking one image or another image, so both the coordination geometry will be, or the center of reference, or like origin will be different. So this translation is just to make sure the origin of both the images has been aligned. So this is just an alignment step. Then 2D to 3D conversion. This is just to equate the number of dimensions, because the lateral image or like side image is having two axes, y and z. So if we are creating or comparing with 3D, so that's why we have to create a 3D variable. We have taken 0. Similarly, PA posterior anterior, that is having two dimensions, x and z, and we have to equate it. So that's why we have included the second dimension 0. So we have created both the 2D image into the 3D for the comparison purpose. That is a software requirement or the implementation requirement. For understanding, you can understand like this, but actually this step is not required, because for the comparison we required only. Then the rotation. uh, Rotation is performed so that the 3D template can be the correspondence can be created or alignment, proper alignment can be created. So here you can see like we have the contours, and this red one, red blue is having a like this is a 3D template. So after rotation, the maximum alignment has been made. Then the scaling, the 3D template and the X-ray image both may have on the different scale. So scaling is very important so that in future we can do the measurement over the pictured 3D surface. Then 3D deformation. This step is similar as we have explained. So once we are able to do the correspondence, rotation, scaling, translation, everything, then we have to create the deformation. So deformation help to just to achieve the projected boundary or uh, projected contours of the uh, 3D template volume. And for the result, we have taken the same parameter like recall, specificity, precision, and accuracy. This TP is true positive, true false positive, true negative, false negative, FN is false negative. These are some qualitative results. Like these are the ground truth, like right side maxillary sinus ground truth, and this is the reconstructed or the constructed by our algorithm. This view. So for the visualization purpose, you can see this looks like the similar one. However, for the quantitative purposes, if you will compute, then the dice coefficient is 0.88, and this is the best case. And we got 0.87, 0.86, 0.85 also. We have taken around 30 patient data and perform use this algorithm and use this procedure and compile the result. So this is just a qualitative view that how the result were received or what kind of result were there. This comparison is with the CT. With the CT, like how we have how it look like in comparison with the CT. Like this is made by us or made by the algorithm, and uh, this is the comparison with in comparison with the CT. However, we have compared it, but actually the comparison is not fair because the CT equation is the different procedure, and this uh, development or this prediction is the different procedure. So while comparing the particular slice, like we don't know which slice is here, and we don't know like particular this nth slice will be matching to this one or not. Actually, the formation of both the images is the different procedure, but we are comparing it for the satisfaction of the user, but actually the comparison is not here, or comparison is not possible because the formation is very different. Here the slice thickness will be different in both the cases, and the scaling can be different. So many things can be there. However, for the satisfaction to the user, we are able to compare it. And from the graph and the quantitative wise, we can see over here. So average accuracy is achieved around 0.83, and with the standard deviation of 0.028, and then DSC value and IOU intersection over union and other parameters you can see over here. Now, after performing this experiment, the challenge was that how to compare. That was the first experiment we have done on the on the maxillary sinus. and that area is very difficult to, so like how to compare or how to show the significance of the work. So what we have done, we have compared our work with the segmentation work, simple segmentation. We have done the prediction task, but we have compared it with the segmentation, like if anyone has taken the CT image or the CBCT image or the MRI image, and then they have segmented it automatically, and what was the accuracy, what level of accuracy they have achieved. So we have compared with that type of experiment. So then we are able to say that we are also achieving the similar kind of result as the literature experiments are getting for the segmentation only, but we are predicting it from the X-ray. So this is outcome of our work. Like we have published the article in Journal of Computers and Biology and Medicine. Also filed one patent, Indian patent we have filed. That is under review. So the challenges, this is very important. The challenge is first one important challenge is the relevant data set. So to get the relevant data set is very important, because here to perform this experiment, we have to get the X-ray images as well as the CT or CBCT images. X-ray images for developing the 3D model or 3D image, and CVCT or CT is for the comparison. But if you will acquire both of them from the same patient, then ethically it is not allowed to give the higher radiation to the patient. Right? So so acquisition of data is very important. Even we also were not able to find the suitable data because of the ethical approvals and all. So what we have done, we have taken the CT images from the clinics, from the AIIMS Bathinda, and then we have derived the lateral PA view from the X-ray image, from the CT image, and using the same procedure as they do in the clinic. So then using the synthetic X-ray images, we have considered them as a original X-ray and then perform the experiment. And surprisingly, like in the literature also, everyone has done the same because of this restriction, right? Because if you are taking X-ray image and CT images from the same patient, then that will be the very high radiation exposure to the patient, and ethically it is not allowed. And another is the feature extraction, like extracting the contour from the radiograph is a bit difficult. This can be done by the expert radiologist or expert orthodontics. And while doing this task, we have done this task manually due to the accuracy constraint. However, in future that can be done automatically. But automatic doing this task comes with the challenge, like if you have not extracted the contour properly, then the accuracy may be compromised. Right. Then similar like finding 2D to 3D correspondence, it may be a bit difficult if the deformed cases are there, or cases with the different age group, or the higher variations are there, so it may be very difficult. And deformation of human anatomy. So again, like deformed cases or the higher variation cases, the deformation may not be accurate. And the unrealized hidden anatomy variance, basically whatever information we are incorporating in the 3D surface image, that is based on the X-ray images which we have observed. But the anatomical variation or the information which is not available in the X-ray, then how to incorporate that information to the 3D surface. So the challenge here is, if the information which is not available in the X-ray, then that cannot be included in the predicted 3D in the predicted 3D surface image. So again, this comes the challenging situation, like then why we are doing it if we are not incorporating new information. Yes, the new information cannot be incorporated, but yes, if we are having two different images or two different segments, and then we are combining them and making it one and creating a 3D visualize, then it will be more useful, and you can say like 2.5D, you can say, or you are giving, or we are able to give the quantitative volume also. So in that way, that will be helpful. So now we are at the verge of the time, so I'm not explaining this systematic review. Any other day we will discuss. I'm skipping this one. Okay, now I am concluding. So to eliminate the significant higher radiations, along with the lower cost and high availability of the imaging modality, the 2D to 3D surface development techniques can be used. So we have discussed two case studies. So thank you. If you are having any question, so all questions are welcome.
Sir, I have one question. In this,
Please.
we have converted for maxillary sinus. Have you done or have you gone through any studies for other sinuses like ethmoid, sphenoid, or frontal?
Actually, this is important question, and sometimes also I also want to discuss with you. Actually, what problem we find that we cannot see it on the X-ray image. We can see
Yeah,
only the
there
maxillary
are
sinus.
yeah.
Yeah, yeah.
Thought there are some particular X-ray views which we can use to see those sinuses like ethmoid and sphenoid. But the thing is ki, and even in if those patients, the purpose of doing this is to operate those patients. And we have seen what happens that in mild to moderate cases, maxillary sinus or maxillary sinusitis disease patients are managed conservatively. But uh, our purpose of doing a scan is to get the surgical anatomy, to know the surgical anatomy for surgical planning, basically operating them for functional endoscopic sinus surgery. So if we are not able to do this for other sinuses, then practical how we can use this technique practically, I am doubtful actually whether we'll be able to use it in a clinical or practical sense or not.
Yeah, actually, this like doing it for the maxillary sinus is the first experiment for the sinuses and in the upper airway area. However, I'm not saying this is this is very much useful, but in cases where the X-ray is not sufficient or extra information is required, then in those cases, this type of experiments are required. I'm not saying that for the surgery cases, but yes,
Mhm.
where the volume is needed to capture, or maxillary sinus, in case of cyst, or in case of like tumor, in those cases may required or extra information may be given. So that's why for a little objective or little significance we have done it, but that is a first step in that direction. If we are able to see the other geometry or other anatomical geometry on the X-ray image, and we can trace it, we are able to trace it on the X-ray, then we will use it, we can use the same method or same methodology for creating the 3D one. So that was our objective.
Okay, sir. And uh, recently, I was attending the global AI summit. It was on Saturday, Sunday. So I had come across one of the clinician from Oman. He was there to present his study. So what he has done in his study, thought that was not related to radiology. He has tried to interpret the echocardiography report from the plain ECG of the patient, and he was able to get so much information. Means he has presented in almost all the domain, but here I am not. Means that will take a lot of time if I'll explain that. But basically, he was using machine learning or other models also. He was trying to interpret the basic echocardiography report from just a ECG. So I feel the practical usability of that thing is more. Means only I feel those studies will be very successful or will be able to make lot of difference where practical usability is more. If you are able to get signers, then it will be very difficult to to use this in clinical practice to make this a big change in the system, in the clinical system, I think.
Yeah, actually, like this is not like creating a maxillary sinus using the X-ray. It's not like this work has been done. This is just a stepping stone. Like this is a first step in this direction. As I've already shown the many experiment in the literature where the people are trying to create it from 2D to 3D at the initial level. But nowadays, you will be surprising to know that some experiments are there where using the two X-ray, they are able to make the 3D volume. I'm not talking about 3D surface, 3D volume, like two X-ray and 3D volume, like head
Hmm.
CT. So they are developing those kind of models using the generative AI. So like we are also planning that one. So I'm trying to say that the research is not ended, or like this work is not ended at this moment. Like this is a finding stepping stone, and then the next level is like if we are able to do it for the small the small volume for the let's say maxillary sinus, then we can make it little big, or like we can do it for the for the head area, or like spine area, or for the femur area, where only two X-ray will be sufficient to create the real 3D real 3D anatomy, or equivalent to CT. So that kind of work is ongoing.
Yes, yes, sir. Regarding this, we used to do, even while I was in Southern 5 years back, we used to, from the simple CT scan of the face, we used to do in a polytrauma patient or in a trauma patient where we are taking those patients for surgery, basically facial fracture, we call it leaf pods fracture. In those patients, we used to do the plain CT scan, NCCT face, and then we used to do 3D reconstruction for knowing the type of fractures and how much, especially in a kind of like when there is a bullet injury on the mandible, on the face, then we used to do this. So that was even before the AI was in AI was very popular. But I am of a higher hope that this will be helping us clinically if we are able to generate a 3D image from just the X-ray films.
Yeah, actually, my idea is just you can see, like from the starting point of view, we are able to think and we are able to create a little bit. Then, in the progressive way, at the like it is audible. Hi, Dr. Krishnan. It is audible.
Yes, sir. Yes, sir. Yes, sir.
Yeah.
I'm here.
Yeah, so actually, I mean to say that if we are able to, if I talk about me, then 5 years ago, I was not able to think like we will be able to create a 3D model using the two X-ray. Then I thought like this is this cannot be possible. but then we collected some data, or we derived some synthetic data, and then 2 years ago we were able to do it. But now we are thinking to create the complete 3D model, and uh, while thinking also we are thinking like it will be happening or not. And if we see the literature, then if you experiment on the spine, they claim that it can be done. So this is like a progressive way, or this is a like a delta increment, or like a delta improvement. So I think in this way the people are doing, and using the generative AI, it will be possible. And maybe at the same time, or in the near future, it will not be directly relevant to the clinical purposes, but later on, after 10 years or more than that, then on some day the people will be able to do it, or it may be aligned with the other features like the virtual reality. It can be added in that way, or for the education purposes. So there may be other applications can be there at the starting point, but later on at the end it will be used for the clinical purpose. So the journey is very long. I'm not saying journey like the problem has been solved. This journey is very long, and we are at the initial stage or at the starting stage.
Yes, sir, sure, sir.
Okay. Any other question from the audience side? Okay, I think there is no more question. Then we conclude this session. And thank you all for listening patiently. Now we will start next practical session at 2 o'clock. Okay, thank you very much.